Example 18. The horizontal steel rod, 2.5 meters long and 1,200 mm squared in cross-sectional area is secured between two walls as shown in the figure. If the rod is stress-free at 20 degrees Celsius, compute the stress when the temperature has dropped to negative 20 degrees Celsius. Assume that 1. The walls do not move, and 2. The walls move together a distance of 0.5 millimeters. Use coefficient of thermal expansion 11.7 times 10 to the negative 6 per degree Celsius, and E is equal to 200 GPa. First, you write the given. L, which is the length, is equal to 2.5 meters. The area, which is 1,200 mm squared. And the change in temperature. Now, change in temperature is from 20 to negative 20 degrees Celsius. So basically, the entire change of temperature is from 20 to 0 and 0 to negative 20. So that's a total of 40 degrees Celsius of change in temperature. Now, our coefficient of thermal expansion is 11.7 times 10 to the negative 6, and our modulus of elasticity is 200 GPa. Now we write what is required. That we are asked to solve for the stress in the material, which is basically the thermal stress. Then we write our solution. Now, for the first scenario wherein the walls is restricted, if you can notice, as temperature decreases, the thermal, the material contracts, right? So if the material contracts, if you can notice, the thermal elongation there is going to the left, right? So, oopsie, please don't mind the adds from the calculator. So that, let's say that is the initial condition. And then once temperature is decreased, this is what happens. Just what I said a while ago, since the temperature dropped, this material contracts, meaning it shortens. So the material now shortens. As observed, the thermal elongation is illustrated there. How the material contracts due to temperature change. Okay, as written there, the actual scenario is the material is fixedly attached at both ends. So therefore, it simply means that although material will contract due to temperature change, in reality, we will not see the material shortening. It's because the rigid walls at the right side of the material exerts an internal force to the thermal stress being uh, equivalent to the thermal stress exerted by the material, so that the material will stay put, well, rather, to maintain equilibrium, so that the wall will not move. So therefore, like I said, the rigid wall at the right side of the material exert a certain internal force, so that the material will maintain its integrity, or but rather will stop the material from moving. So that is how we can analyze this problem. So that is why the internal force there, the wall exerts a certain amount of force, and from that we can establish our compatibility equation. As you can observe, our compatibility equation is the thermal elongation is equal to the elongation due to the internal force exerted by the rigid wall. Now we can substitute our formulas. If you can notice, the thermal elongation formula that I used here is alpha times the change in temperature times L, right? But as provided in the previous video, on the lecture video for thermal stresses, you can always have it interchanged, so that it follows the acronym ALAT for much recall, much easier, a formula that is much easier to recall. So interchanging rearranging the variables, we can now have our thermostress is equal to alpha times change in temperature times E, and now we can substitute the values. 11.7 times 10 to the negative 6 for our alpha. Change in temperature is 40 degrees, and our E, or our modulus of elasticity, is 200 times 10 to the ninth power, or gigapascal. So if you can notice here in the calculator, you can always refer to the calculator on the left. Now if you can notice, there are a lot of zeros because that is in the base unit, which is Newton per meter squared. So that's 93,600,000 Pascal, or basically 93.6 megapascal. Or we can have it in 200 times 10 to the power of 3. That's if 200 times 10 to the power of 3, that is Newton per mm squared, which is still in megapascal. So there you have it. Your answer is 93.6 megapascal for A. The walls do not move. Next, how about if the wall moved together a distance of 0.5 mm? As provided in the procedure, it is best that we do some sketching, so that it will help us in solving the problem. It can really help doing some sketches, some diagrams. Okay, that's the initial condition. So after the temperature changed from 20 degrees to negative 20 degrees Celsius, the material, at the same time the wall, moved together with the a difference of zero point 0.5 mm. Should be an mm. Or is it zero point 0.5 meters? Okay, so that is where our material is now. It moved at the distance delta. So not just that, as the wall moved, the material also still deforms due to due to the application of change in temperature. Okay, so basically what this means is our material is fixed at both ends. Now, if let's say the material is not fixed, the the first, second, third figure here, the point where the material is now, that would have been the point where the material will be if it is not fixed. However, it is fixed. Therefore, the wall will exert a certain internal force P so that the uh, the wall will prevent the material from really moving towards that new point, right? But since they are playing tug of war, I'm sorry for the lack of better word, tug of war, since the material contracts, it pulled the wall with it by zero point 0.5 meters. But nevertheless, there is still an internal force that manifested within the material due to the fact that the material is fixedly attached to the wall. So that is why if you can notice, our compatibility is the entire thermal elongation is equal to the elongation due to the internal force P, or thermal elongation sub P, plus the movement of the wall, which is delta here. Now rearranging our formula for applying Hooke's law, then we have stress is equal to E multiplied by the quantity alpha times change in temperature minus the difference in position over L. Now we are to substitute our formula. So that's stress is equal to our modulus of elasticity, which is 200 times 10 to the power of 3. I know that the E provided is in gigapascal, but if we are to use times 10 to the third power, it simply means that's 200 times 10 to the power of 3 megapascal, or Newton per mm squared. Next, we substitute our alpha, which is 11.7 times 10 to the negative 6. And then our change in temperature, which is 40. Oh yeah, just to make some corrections, our change in change in the difference in distance is 0.5 millimeters, not meters. Okay, and then our L, or the entire length of the material, is 2.5. I believe this is in meters, so we have to multiply that by 1000. So just to make some corrections, that's times 1000 exactly. Okay, we can now input everything in our calculator. Now I know that to some of you, with many numbers, you cannot directly input everything in your calculator. So what you will do is you do multiplications first, right? Or you do the parentheses first, following PEMDAS. For those whose calculators are not that advanced, wherein you cannot input everything in one go. But however, if you have that kind of calculators, then there's nothing wrong with inputting everything all at once. So our final answer now is 53.6 Newton per mm squared, which is 53.6 megapascal. Thank you.